let us get into the location problem formulation, and let us look at all the dimensions of it. So the first thing that matters when we are solving the location problem is how are we going to measure distances, right? Location problems are heavily dependent on the way the geography is modeled. Right, I'm thinking about two-dimensional plane where I'm trying to decide the facility. It may be a map of the city, map of the country, right? If you're talking about global supply chains, the world is your playground. But essentially, you're talking about a two-dimensional graph and some kind of a network on it, where the warehouse is connected to the factory and warehouse is also connected to the retail store and all that. So, what matters is on this two-dimensional graph, on this 2D graph, every location is going to have coordinates as xy. How are we going to measure distances between 2 points on this graph, right? How are we going to measure distances on this graph? So let us say there are 2 points, xi, yi, xj, yj, 2 points. This is your location. This is the map of the area. This is point number 1. This is point number 2. So this is point number 1. This is point number 2. Point 1 is xi, yi. Point 2 is xj, yj. Right? How are you going to measure the distance? Euclidean distance measure is a well-known measure of distance, and it simply measures the distance as the bird flies. Right? As the bird flies, straight line. As a straight line. Right? So that's exactly how the distance is measured, as a straight line. Euclidean distance measure, right? And you know that formula is fairly well known. Sometimes, particularly in facility location problems that are modeled within a city, we may want to use a different measure, because Euclidean distance measure says that there is always a road that connects point A to point B. What if there is no road, right? Particularly when you are locating facilities within the city, how can you guarantee that there is a straight line connecting road point 1 and point 2? You cannot guarantee. So in those cases, you may have point 1 connected to point 2 only as a network of roads, right? Here there may not be a direct straight line, which is the red line. So Euclidean distance measure may not even help you understand the distance. So the real distance is how the truck would go from point 1 to point 2, how the truck would go from warehouse to the retail store, how would the last mile delivery person take the bike and go from restaurant to the location of the customer, right? In a food delivery system. So then the distance is only measured in terms of the roads, right? And that distance measure is called metropolitan distance measure, which is essentially the difference between x coordinates and the y coordinates. It essentially says that road networks in a city, it assumes that the road networks in a city is a grid of horizontal and vertical lines. So if you are talking about a location here, if you are talking about a location here, so this is, let us say that I am talking about these 2 points. Let us say that I am talking about these 2 points. So this is my point number 1, this is my point number 2. Metropolitan distance measure would say that first I will go y distance, which is coming down here, and then I will travel x distance. So what is the distance between point 1 and point 2? This is the distance horizontally, which is this guy. This is the distance vertically, which is this guy. So this is called a metropolitan distance measure, which assumes that the road network in a city is a grid of horizontal and vertical lines, right? And therefore the distance can simply be separated as x distance traveled and y distance traveled, right? And obviously there is no direct road, right? There is no direct road connecting the two, right? Otherwise I would have traveled on that road. I would have traveled on that road. So metropolitan distance measure also may be relevant in some cases. Smaller locations, smaller areas where I have a nice grid of roads, right? Think about a well-planned city, something like New York comes to my mind, right? very nice structure of vertical and horizontal roads, right? And there you can use there the only way to measure distance is to decide how much I have traveled horizontally and how much I have traveled vertically, right? And add the two. And unlike Euclidean distance measure, I cannot separate the x component and y component. In a metropolitan distance measure, I have nicely separated the x component and y component, right? That matters, and I will show you in couple of slides why does that matter. So what is the first important dimension to be considered in location problems? How are we going to measure distances, right? Are we measuring distances using the square root formula or the separation of x and y coordinates? Second thing that matters is the number of facilities. I already spoke to you about this. If you are you trying to decide that one single factory, one single facility will serve the entire consumer base? Those problems are slightly easier problems, right? Single facility location problems can be solved with slightly more ease, and those are the first problems that we are going to discuss immediately now. However, most of the practical scenarios may require us to have multiple facilities, right? No manufacturer today has a single facility that serves the entire consumer class. They always try to go closer to the market, and therefore may want to have multiple facilities, right? Multiple facilities, multiple manufacturing sites, multiple warehouses, definitely multiple retail stores. So multiple facilities, they are difficult problems to solve, right? Not only because the number of facilities may not be known, right? You tell me, should I have 3 facilities, should I have 4 facilities? So I won't even know whether I am trying to solve a 4 facility location problem, whether I am trying to solve a 5 facility location problem, because the problem, the mathematical model should tell us how many facilities should I have. And the other complication is the type of facilities. The type of facilities may also vary, right? The type of facilities may also vary. For example, as I told you earlier, demand may have geographic flavor. In certain geographies, certain products sell better. Certain other products sell better in certain other geographies. So I can't have the same manufacturing facility copy pasted in multiple locations. Now, and since each of these facilities may be manufacturing different set of products, the facility location may be governed by those products. For example, some products may require lesser space, some products may require more space. All those things have to be considered, and therefore the type of facility may also vary, right? The type of facility may also vary. Let us think about let us think about food supply chain, right? Food supply chain. Now you know that Food Corporation of India (FCI) has large number of warehouses spread across the country. They are predominantly used to store grains, right? Wheat and pulses and all that, jawar and bajra and so on, right? Now we can classify those type of warehouses as similar, right? Not the same, but similar. If I am storing grains, certain requirements are similar, and therefore I can group them as saying that the warehouses will be similar. What if agent in the food supply chain or is also in the business of vegetable supply chain in addition to the grain supply chain? Now the warehouse required to store vegetables or fruits is going to be very different than a warehouse required to store grains. First of all, you may require cold storage to make sure that the vegetables live longer. Most probably the grain storages don't require cold storage. I mean, you all obviously have to protect them from the nature, from the weather. You don't want grains to get soaked in rain. But grain storage may not require cold storage, whereas fruit storage may require cold storage. Therefore, you are talking about type of facilities, right? Type of facilities. So, multiple facility location problems are inherently harder problems because of all these issues. So, this is the second dimension, right? Number of facilities matters in a facility location problem. The third thing that matters is who is actually solving the problem, right? For example, if a private entity is trying to solve the problem, now their objective may be profit maximization. Whereas if a government agency is trying to solve the problem, their objective may be maximization of social welfare, minimization of cost, right? And these objectives do matter. If the objective function is different, the solution gets different, right? So it matters, right? The optimization criteria does matter. So are we trying to only say that, well, I am trying to make sure that my consumers are not inconvenienced, and therefore my objective is always going to be to reduce their travel time, reduce their travel cost. I am a government agency and therefore I really should not be worried about profits. That's a school of thought. I don't know whether that is the correct way to think, but anyway, their optimization criteria may be to maximize social benefit, right? Their criteria may be to maximize utility. How do you measure utility is also going to be an important question then, right? So all this matters in facility location problems. All this matters. So we have seen three different components that matter in a facility location problem. The distances. How are we measuring the distances? How many facilities have to be located, and what is the optimization criteria, right? Plus all those constraints that we earlier spoke about, they may also matter. Right now in our discussions, we are not going to include those hard to model constraints. Let us look at the basic formulation first, then we will make it more and more complicated. Now let us start with a very simple problem, right? And I have a nice example for this. I live in Chennai, and one of the tourist attractions in Chennai is our Marina Beach, one of the longest single stretch beach, right, in a city. So let me change the color. So let us say this is the beach, right? Obviously, this is where the sea is, and these are the roads, right? These are all the roads, and these are bus stops and all that, right? And this is the sand. This is the sand. This is my beach. Now think about bhaji vendor, right? Think about a guy who wants to sell butta. I hope you have eaten a butta on a beach, right? Nice things to do. Right, let us say that there is a vendor who is selling balloons, for example, right, on this beach for the kids to play with, right? You often see them on the beach, balloon sellers. Now let us say that there is a vendor who is trying to decide where should I stand, right? I'm a single vendor, right? I probably have a small setup where I can have my gas stove and everything, and I can fry some peanuts. I can heat up some buttas, right? Or I can make some tea. Should I locate my stall here? Should I locate my stall here? Should I locate my stall here? Right? I'm just a single guy. I don't have any franchisee. Right? So that problem to me is a single dimension, single facility location problem. Why is it a single dimension? First of all, because it doesn't matter whether the guy is located close to the sea or close to the road, right? I mean, what matters is people are going to be walking along the beach. People are going to be walking and sitting along the beach. This distance is not that great, right? This distance typically is not that great, and therefore this y dimension, if you think of this as x and y, right? This y dimension doesn't matter much. This y dimension doesn't matter much. What matters is where do I locate my facility on this beach, on this horizontal axis. Therefore, to me, this looks like a single dimension problem. As I told you earlier, there is a single vendor who is deciding where to put her stall, right? Where to put her stall. Therefore, this is a single facility location problem. We are not worried about having 3 or 4 tea stalls by the same person. This person is deciding where to have the tea stall on the beach, right? Now there may be competition. Right now the objective is not to look at competition. Let us have a decision theoretic formulation where this person is deciding where to locate, right? So what do you think? Intuitionally, what do you think should happen? Obviously, you want to locate your stall where you think where you think maximum number of people are sitting, right? Now let us say that some portion of the beach, they have some garbage collected, right? So if this area is all garbage and so on, very unlikely that people will be sitting right next to a dump of garbage, right? And therefore the density of your potential consumers here in this region may be lesser, whereas probably the density of your consumers sitting here may be higher. So if you want to maximize your sales, you want to be closer to the consumers, right? And therefore you want to sit, you want to have your facility where most of your consumers are sitting, because we are assuming that consumers may not want to travel longer distances to get a cup of tea, right? By the time they come back to the family to have tea together, the tea would have been cold, right? So the travel along this horizontal line also matters for the consumers. So so what we are going to do is we are trying to find a single location for a single facility, for a single vendor on this beach. Now for that, what we are going to do is we are going to arbitrarily select a point. So let us say this point is my proposed location. This point is my proposed location, right? So how should I solve the problem? Let us say that I split the entire beach in multiple sectors. Each sector may have a demand density. Let us call that demand density as Wj, the weight of demand in each of these clusters, each of these zones, if I want to call them, right? And from this zone, if I am having a facility here, the person has to travel, right? The person has to travel from this zone to this facility. From this zone to this facility, the person has to travel. From this zone to this facility, the person has to travel. From this zone to this facility, the person has to travel. Customers have to travel. So let us say that this vendor is very considerate and doesn't want the consumers to travel longer distances, because if you make them walk longer distances, they are simply going to give up and not come to you, right? So it does matter to your sales. You are not only being considerate to your consumers, you are also being very, very conscious of your profits. So how would you solve this problem? So essentially all the locations before this are going to travel in this direction. All the locations of all the consumer locations, right? Consumer locations are going to travel in this direction, right? So people here are going to travel in this direction, people here are going to travel in this direction, right? And this is where your facility is. Right now we don't know where S is. S could be here, S could be here. Right now we are saying that this is where my facility is. So if you want to minimize the travel distance, the weighted travel distance for the consumer, your objective function is going to be Wi, which is the weight, the relative demand at location I. As I told earlier, what is this location I? Location I is the zone on the beach where people sit, and you are worried about the demand density in that particular zone, right? So I could have said this as zone I. S minus x, because here, can I remove some of the clutter? Right, let us draw this all over again. I tried to explain this, but let us draw this all over again. So this is the beach, this is my sea, these are the roads, this is where parking is probably, right? Then I have decided that this is where my facility is, and let us say this is this is zone 1, zone 2, zone 3, zone 4, zone 5, zone 6, zone 7, zone 8, right? So location of, so let us say that arbitrarily, let us say this is my origin, this is my 0, this is my S. Anyway, this is a single dimension problem, so this is my x-axis, and I am thinking that on this x-axis arbitrarily I have set the origin to be here. I could have set the origin anywhere. So what is the x coordinate of my facility? Let us say my x coordinate of the facility is S. What is the x coordinate of the zone 1? Let us say this is x1. For zone 2 it is x2, for zone 3 it is x3, for zone 4 it is x4, zone 5 it is x5, zone 6 x6, and so on. So what is the distance that zone 1 consumers have to travel? The distance that they travel is s minus x1. And how many consumers potentially you want to take this distance? You want wi number of consumers or w1 number of consumers to take this travel so that they can come and visit your facility. So what is the weighted distance then? S minus x1 multiplied by w1 is the weighted distance of all the people traveling from zone 1 to your facility. Now similarly, S minus x2 w2 is the weighted distance from the zone 2, right? S minus x3 into w3 is the weighted distance. S minus x3 into w3 will be the weighted distance, right? So all the way up to here, up to zone 4. Now from zone 5 onwards, this x coordinate is larger than s coordinate, right? Coordinate of your facility. Therefore, you cannot be talking about distances like this. It will be negative distance. So you take x5 minus s multiplied by w5 is going to be the weighted distance of zone 5. x6 minus s multiplied by w6. x7 minus s multiplied by w7 and so on, right? Multiplied by w7 and so on. Now the question is, how do I know that after zone 4 I have to take x5 minus x and before zone 4 I have to do s minus x4? I don't know, because this s is not known yet. I don't know the location of the facility. This s was arbitrarily decided. So how many of these locations should be on the left of the facility and how many of these locations should be on the right side of the facility? We don't know. So these are the total number of zones. Right? So this m are the zones which are on the left of the facility, and starting m plus 1 to n, those are the zones which are on the right side of the facility. So I don't know, right? I don't know which one is it, but I can still solve this. I don't know where s is, and therefore I don't know what this m is. I don't know. I can still solve this, and if you take a simple partial derivative with respect to s of this optimization objective, you get actually s is of the power 1, and therefore it vanishes. And therefore, what is this recommendation? What is this optimal solution? Ideally, I would have hoped to get an equation like this: s star equal to something, right? I was hoping that the optimization problem tells me what should be the optimal location of my facility. What should s star be? I did not get it in this format, but I got it indirectly. So, what is the optimal solution? Optimal solution, the optimal location of the facility should be such that the total weight on the left of the facility should be equal to the total weight on the right side of the facility. The total number of customers on the left of the facility should be equal to the total number of customers on the right of the facility. Now, if you think that this zone is the most crowded zone, probably because parking is nearby, people don't want to walk, simply park the car and go to zone 8. If you think that zone 8 is going to have the maximum density, most probably your location of the facility will shift closer to the zone 8. That will actually mean more travel for consumers sitting in zone number 1, but we are assuming that there are less number of consumers sitting in zone number 1 compared to the number of consumers sitting in zone number 8, and therefore the facility will get pulled towards the zone which has more population density, right? And here by population I mean that more interested consumers who may be interested in buying my products. Okay, so this is the solution, right? This is the solution. How should I locate the facility? You should locate the facility such that the weight on the left hand side, the total weight on the left hand side is same as the total weight on the right hand side, right? So this is a single dimension, single facility location problem, and the optimal solution turns out to be that locate the facility such that it completely balances the population densities, and then you realize a very important feature of this solution is xi don't play any role. Xi's don't play any role. The travel distances doesn't seem to matter. Xi indicates in some way travel distances, whereas the optimization formulation The objective function was minimization of travel distance, minimization of total travel distance, weighted travel distance. But we are saying that, well, xi's don't play any role in our optimal solution, right? Very, very counterintuitive result. Anyway, that's the result.